Hello students, welcome to my YouTube channel, and today in this video we are going to start a new topic, optoelectronic junction devices in the chapter semiconductor devices. In the last video we have seen about the working of PN junction diode as a half wave rectifier and full wave rectifier. Basically we have seen the application of PN junction diode as a rectifier, half wave rectifier and full wave rectifier. Now today we are going to study about the optoelectronic optoelectronic junction diodes. So first we will see what is optoelectronic junction diode, or basically we can say devices. In so optoelectronic junction diodes. So first we will see what is the definition of the optoelectronic junction diodes. The semiconductor diodes, the semiconductor diodes in which charge carriers in case of diode are basically electrons and holes. Charge carriers are generated by photons, or we can say by the photo excitation, by the radiations photo excitation, are known as optoelectronic junction devices. The examples of optoelectronic junction devices in this topic, basically we are going to study about the three types of optoelectronic junction devices in this topic. The first is, the examples are, the first is photodiode. The working is based upon the photo excitation, and this photodiode, they are used as sensor, used for detecting optical signal. So basically photodiode are used for detecting the optical signal. And number two is light emitting diodes. Light emitting diodes, LED, we call in short form LED, light emitting diode. And third is your photovoltaic devices, they are also known as solar cell. So basically light emitting diode, LEDs, they convert electrical energy into light energy. Light emitting diode, they converts electrical energy into light energy. And solar cells, they convert light energy into electrical energy. Light energy into electrical energy. So one by one we will see all these optoelectronic devices. So the first is we are going to see about the first optoelectronic devices in this topic. The first is photodiode. So basically a photodiode is a special purpose PN diode which operates in reverse bias condition. So basically photodiode operates in reverse bias condition when the light energy or the energy of the photon we represent E is equal to h nu greater than the energy gap E naught of the semiconductor fall on the junction of the diode. Electron hole pairs are generated near the junction by the absorption of the light. Due to external field, they separate before recombination. If an external circuit is connected, we can get an EMF. The magnitude of the photocurrent is directly proportional to the intensity of incident light. So let me first draw the circuit diagram. So photodiode. Suppose we have this diode, photodiode. Let me explain the working of this photodiode. So basically it is a special purpose PN junction diode. Just wait for a minute. It's not going properly. Just wait for a minute. Yeah. So photodiode. First we will draw the diagram of this photodiode. Let me draw this P-type. This is your P-type semiconductor, and this is our N-type semiconductor. You can see it there. We have N-type semiconductor. This is my N-type semiconductor. Okay. Now this is the space region near the junction. This is the junction area. We can represent this is the junction. This is our junction. So this is our junction. You can see it there. This is the junction area. This is our P-type, and this is our N-type semiconductor. This is our P-type, and this is our N-type conductor, and this is the junction. This is the area near the junction. You can see it there. So in P-type semiconductor, holes are majority charge carrier, and in N-type semiconductor, electrons are majority charge carrier. Now what we are doing, now this junction it is illuminated by suppose the light energy, okay, or the energy of the photon. Now this junction it is illuminated by the light energy. E is equal to h nu. Here you can see it there. E is equal to h nu, energy of the photon. So if this energy E is equal to h nu, the energy of the photon, it is greater than the barrier potential, or basically we can say that the junction there is a energy barrier in case of the semiconductors if this h nu is greater than the energy gap of the semiconductor E naught. Okay, energy gap of the semiconductor, then what will happen, this h nu energy it will be absorbed by the holes, and this energy it will be absorbed by the holes and the electrons. These are the holes, you can see it there. Holes in the p side, they are majority charge carrier, and this is the electron, they are the majority charge carrier in n-type semiconductor. Okay, so basically what will happen, these charges basically they will separate before the recombination if we will connect an external source like this. Suppose now we are connecting, what we are doing, now we are connecting an external source here. You can see it there. If we can connect, here we are connecting a battery. This is our resistor. Load we can connect here. can see it there. Now what we are doing, now we are connecting a battery here. This is your battery. Okay, it is reverse biased, so negative terminal is connected with the p type and positive terminal it is connected with the n type semiconductor. And this is our resistor R, external resistor, and here your one ammeter is there. This is your microammeter. This will detect the current. So simply what will happen when the energy of radiations, we can say, if energy of the photon or light energy of photon, it is represented by E is equal to h nu, where nu is the frequency of the radiation, is greater than the energy gap E naught of the semiconductor. Then what will happen? Semiconductor electron hole pair will generate electron hole pair will generate near the junction. And if you will connect a biasing cell or battery there, then what will happen? Before the recombination, what will happen? They will separate. This positive charge will move towards the negative terminal. You can see it there. This positive charge will start moving to the negative terminal. You can see it there. This positive charge will start moving towards the negative terminal. They will not recombine, and this negative charge will start moving towards the positive terminal, and this will lead to the current that is known as photocurrent. So basically what will happen, we will get a current in this external circuit, and this current is basically we are getting because electrons and hole pairs, these charge carriers are generated due to the photon. So the current that we are getting in the external circuit, this is known as photocurrent basically. So here it is photocurrent, and this photocurrent I, it is directly proportional to the intensity of the light that is falling on the junction. So basically this photocurrent, it is directly proportional. Photocurrent I, it is directly proportional. No, let me do with the small symbol I am taking small I. It is directly proportional to the intensity of light. If you will plot a graph between current and potential difference, external potential suppose we are taking, because it is reverse bias, now we can plot a graph. In third quadrant we can plot a graph. Okay, this is the graph we are plotting. Along x-axis we are taking the potential difference, along y-axis I am taking the current. This is your potential difference, reverse bias, negative direction, and this is your current. In third quadrant basically we are drawing. So what will be the shape of the graph? The shape of the graph we will get like this. This is the shape of the graph that we have seen in the modern physics when we are dealing with the photoelectric effect. So this is the intensity I1. Okay, this is the saturation current, and similarly if you will go on increasing the intensity, the saturation current will also increase, and this is your intensity I3. Intensity capital I am representing for intensity I1, I2, I3. So if you will keep on increasing the intensity, the maximum current will also increase. Here I3 is greater than I2 is greater than I1, and you can clearly see that the photocurrent is directly proportional to the intensity of light. So this is all about the photodiode. Now photodiodes are basically used in case of, they are used as a sensor in many of the modern technology to detecting the signals, optical signals. Like in case of lifts, automatic lifts, we are using the photodiode for its operation. Now the next type of the optoelectronic device is the lead. So second is the lead. Now second topic we are going to deal with the lead, light emitting diode. So basically it is a heavily doped PN junction diode which operates under forward biasing. It converts electrical energy into light energy. Lead, it is also known as light emitting diode, light emitting diode, and its function is to convert light energy, sorry, it converts electrical energy into light energy. So basically lead converts electrical energy into light energy. So basically light emitting diode, it is a heavily doped PN junction diode. So lead is basically a heavily doped PN junction diode, PN junction diode, which operates in forward bias condition, forward biased condition. Now let me explain how it is working when we are supplying the light in, when it is forward bias, when we are supplying the electric energy, how the light electrical energy is converted into light energy. So suppose this is our lead, it is a special purpose PN junction diode. This is the p type semiconductor. It is heavily doped, means number of electrons and number of holes, they are very high in concentration. And this is our n type semiconductor, you can see it there. This is your n type semiconductor, and this is the space, or this is the area near the junction. Okay, so what will happen, you can see it there. Now in p type semiconductor, these are the heavily doped, these are the holes which are majority charge carrier in p type, and these are the electrons. In n type semiconductor, electrons are majority charge carrier. These are the electrons, you can see it there, they are majority charge carrier. This is our p type semiconductor, this is p type, and this is your n type. It is heavily doped. Now what we are doing, now it is forward biasing, we are forward biasing. Now this p type semiconductor, it is connected with the positive terminal of the cell, and this n type semiconductor, it is connected with the negative terminal of the cell. And this you can see it there. We are supplying the electrical energy. Now you can see it there. This is your p positive and this negative. So what will happen, this positively charged, the positive terminal of this cell, what will happen, it will repel these holes from p type to enter into the n type. They will move and they will try to enter into the n region. Like this they will start moving. Negative negative repulsion will be there from this side, and positive positive repulsion will be there from this side. And what will happens, near the junction, what will happen, the diffusion of the electrons and the holes will take place. This is the area near the junction. Okay, the positive charge, what will happen, the positive charge will combine with the negative charge, negative charge positive charge, negative charge positive. Here the diffusion will take place. Diffusion of because it is heavily charged particle, heavily doped, p side and n side are there, so diffusion of electrons with holes will take place, and due to this diffusion what will happen, the light energy will be emitted. Okay, so due to the diffusion of the electrons with the holes, what will happen? The light energy will be emitted. The light energy here the emitted E is equal to h nu, it will be emitted. Here we are supplying the electrical energy. What we are supplying? We are supplying electrical energy, and what we are getting? We are getting light energy, electrical energy, and now we are getting light energy. E is equal to h nu, which radiations you will get, that is light energy. Okay, thus we have seen that uh, this LED light emitting diode, how it is working, just we have seen. Now what are the advantages of this uh, LED over the general types of the lamps that we are using? So number one is the low operating voltage and less power. These are the advantages of the LED. Now nowadays LED is frequently used everywhere due to the following advantages. Number one, low power consumption, low operating voltage. Okay, at low voltage it can operate. And number two, low power consumption. That's why the cost of electrical energy, it will be also less. Low power consumption. Monochromatic, it produces a monochromatic source, monochromatic light, means single frequency light it can emit. Monochromatic, now LEDs are available in different colors, also white, red, green, yellow, whatever type you want to get, you will get in the market, but of single frequency. Long life, it can operate for long duration of time, long life. And fast on off switching, fast on off switching capability. So these are the advantages of the LED over the general types of lamp that we were using before. So this is the main advantages of LED. Now moving to the next type of the optoelectronic devices, that is our solar cell. So the next type of the optoelectronic devices that we are going to discuss is solar cell, or it is also known as photovoltaic cell. Photovoltaic cell. So basically solar cell, it converts light energy of the light into photodiode. You have also seen they are also converting light energy into electrical energy. Electrical energy. Now in the previous case of when we are discussing about the photodiode, we have also seen the photodiode is also converting the light energy or the energy of photon or the energy of radiations into electrical energy. But what is the basic difference between this solar cell and the photodiode? So the only difference between the photodiode and the solar cell is that in case of photodiode we require an external biasing, but in case of this solar cell no external bias is required. Okay, this is the simple difference between the photodiode and the solar cell. Now moving to the next topic, this topic we are discussing. So basically a solar cell is basically a PN junction which generates EMF when solar radiations fall on the PN junctions. So basically solar cells or solar cell is basically a PN junction which generate EMF when solar radiations solar radiations fall on the PN junction. Fall on the PN junction. It works on the same principle, on the same principle as the photodiode, except that no external bias is applied in case of solar cell. Now, the generation of EMF in the solar cell by the solar cell, when light energy fall on it, it is due to the following three basic processes. Basically, three processes are involved in the generation of EMF. The generation of EMF by a solar cell when light falls on it, is due to following three processes. Number one is generation. The first process is generation. The first process is generation. Generation of electron hole pairs due to light. Light h nu, the energy of light must be greater than the energy gap of the semiconductor diode, Eg. First is the generation. When the light energy falls on the solar cell, there will be generation of the electron hole pairs. Number one. Number two is the separation of electron and the holes due to electric field of depletion layer. Due to electric field of depletion layer. We have already discussed about the depletion layer. It is found near the junction. Okay, this is the second process, and third is the collection. First is the generation, separation, and collection. The electrons reaching N side of the PN junction, N side, are collected by front contact. I will explain what is front contact. And holes reaching P side are collected by back contact. So these are the three processes which are involved during the process of generation of EMF by a solar cell. So first is the generation, in which electron hole pairs are generated. And how these electron hole pairs are generated? When the light energy greater than the energy gap of the semiconductor diode falls on the PN junction or to the PN junction diode. Next is the separation. Once the electron hole pairs are generated, they are separated due to the electric field of the depletion layer. And third is the collection. Now collection are electrons that is reaching towards the n side are collected from front contact, and the holes reaching p side are collected by the back contact. So these are the three processes which are involved during the process of EMF generation by a solar cell. So just let us see the diagram. So this is a diagram of, I'm drawing a diagram of solar cell here. You can see it there. You can see it there. This is your N-type semiconductor and this is your P-type semiconductor. N-type and this is your P-type, and this is your top surface. You can see it there. This is your top surface. This is known as back contact. You can see it there. This is your back contact, and this is your front contact here. Basically metallized finger electrodes. Here the electrodes are there. And these are the electrodes. You can see it there. The finger electrodes are there. This is basically your metallized finger electrodes. Okay, and this is the energy of the radiations. The energy is falling on this semiconductor diode is equal to H. It is falling on this solar cell is equal to H. Okay, now we will see the diagram. This is your P, this is your N, PN junction, and this is the depletion layer. This is your depletion layer. This is your P type, and here it is your N type. Now just connect P and this N. Okay, it's a positive. Sorry, this is your, here we can connect one load here. Then current will start flowing. The load current will be equal to IR. Okay, so this is the working of the solar cell. So this is all about from the today's topic. So today we have seen about the optoelectronic devices, junction devices, and the three types of optoelectronic junction devices we have seen. First is the photodiode, second is the light emitting diode, and third is the photovoltaic cell. So that's all from today's. Now we will see the next topic when we will come in the next class. Thank you everyone for watching.